Hello everyone, welcome to the lecture series of acids and bases, and here in the lecture number 13 I am going to deliver a talk on solid acids. Acids are generally found to exist in the liquid state such as acetic acid, sulfuric acid, etc. But there are numerous examples of acids which are solids in ordinary temperature. For example, benzoic acid, oxalic acid, etc. Now these solid acids can be categorized into two classes such as organic solid acids and inorganic solid acids. Most of the organic solid acids have this carboxylic acid group, bond COOH, and examples of such acids are benzoic acid. This is definitely a solid at room temperature because it will melt at 122.3 degrees Celsius, that is much above the room temperature. Another one is phenylacetic acid, melting point 76.5 degrees Celsius. So this is also very high temperature rather than the room temperature. Then orthonitrobenzoic acid, 147.5 degrees Celsius. Phthalic acid, that means benzene 1,2-dicarboxylic acid, 210 degrees Celsius. Isophthalic acid, that is benzene 1,3-dicarboxylic acid, very high melting temperature, 342 degrees Celsius. Terephthalic acid, that means benzene 1,4-dicarboxylic acid, 300 degrees Celsius, it will melt. And oxalic acid dihydrate, it will melt at 101.5 degrees Celsius. Now just have a look on the solubilities of these acids. They are poorly soluble. Out of this, only oxalic acid has a good solubility, 118 gram per liter, because this is a dibasic acid. Also there are 2 molecules of water in its crystal structure, but others are very poor, sparingly soluble in water. And not only that, after dissolution they can hardly produce protons. They are very weak proton producers, so they are very weak acids. Now inorganic solid acids, they are generally hydrogenated salts, and these hydrogenated salts have the examples such as cesium bisulfate, cesium biselenate, cesium dihydrogen phosphates, etc. Now they have a special character of superprotonic phase transition at elevated temperatures. So they belong to a small class of compounds that exhibit superprotonic phase transitions at slightly elevated temperature. For example, cesium bisulfate transforms at 206 degrees Celsius into a superprotonic phase in which both protons and oxygen atoms partially occupy many sites. They are highly conductive in the solid phase and do not need the presence of water. This fact renders them attractive as electrolytes for solid acid fuel cell application. Now, in contrast to cesium bisulfate, the solid acid cesium dihydrogen phosphate does not appear to undergo superprotonic transition. The difference in behavior between the sulfate and the phosphate is related to the difference in the extent of bonding between oxygen atoms rather than to chemical differences between sulfur and phosphorus. It may be explained in such a way that entropy drives any solid acid to a high temperature structure, in which all oxygen atoms participate equally in forming hydrogen bonding. And this is the structure where if the ratio of hydrogen is to sulfate or phosphate ratio is precisely not equal to 2:1, then such chemical equivalence of oxygen atoms can only be achieved if the structure transforms to a state in which proton occupancies are less than 1, or oxygen site occupancies are also less than 1, or both. And this disorder simultaneously leads to fast proton transfer in the high temperature phase and thus superprotonic conductivity. So that's all about the solid acids, a precise idea about that. Thank you. Have a nice day.